Okay, I think let's begin. So, welcome everyone again to the second day of this workshop on high performance analog and mixed signal VLSI system design. So, I hope you had a informative session yesterday. So, today we will be discussing, we'll start with fully differential amplifiers in this session. The second session will be by Dr. Vinayak again on voltage reference circuits. And then in the afternoon, we'll have a session on sample and hold circuits, and followed by the lab session in the evening. Okay, so we'll begin with fully differential amplifiers. So first thing is what are fully differential amplifiers? Differential amplifiers we have seen yesterday, right? We had seen many variants of differential amplifiers with different ways of stabilizing them. So essentially, differential amplifiers are amplifiers wherein the input is differential and the output is single-ended. That is all the circuits that we have seen yesterday. I think with the exception of one small one which Dr. Vinayak had shown, all of them had a differential input and a single-ended output. So that is what most of the circuits that we had seen yesterday was. And what I've shown on the right is the most simple form of the differential amplifier two-stage op-amp that we have seen yesterday. And this C here is the compensation capacitor. Yesterday we had seen that this introduces a zero and you can compensate. You can cancel the zero by putting a resistor in series and so on. So this is the circuit we have discussed in detail yesterday. So today we want to move on and look at circuits which have differential input and differential outputs. So a fully differential amplifier is one in which the input is also differential and the output is also differential. So these configurations are useful in high-speed circuits like filters, transceivers, etc., where immunity against power supply and ground noise is desired. So if you have whenever you have differential signals, you might commonly have heard that any noise appears as common mode and therefore it can be easily rejected. So when you are having very high-speed circuits, especially when you have circuits inside a chip, high-speed circuits inside a chip, it's generally desirable to have fully differential signal chains throughout, so that at any point, even if you have some noise on the power supply or noise on the ground, it can be rejected by the high CMRR of the subsequent stages. So how do you make such a fully differential amplifier? Let's take a simple example. I think we all are familiar with a simple differential amplifier which can be constructed using resistive loads. So this is a very basic circuit which we have seen in most of our probably studied in our undergraduate curriculum also, right? So simple circuit, you have a tail current source which fixes the bias point of the circuit, and a differential pair, we say M1 and M2, and two resistors which make up the load of the amplifier, and the gain of the circuit is minus GM into RD. So this is the most simple form of a differential amplifier, in which the input is differential and the output is also differential. So this architecture is often used when we need fully differential amplifiers with low gain and very wide bandwidth. Okay, so you cannot make the gain of this very high. What the gain of this is minus GM into RD. So GM, of course, will be limited by how much current you can pump into the circuit here, and what is the maximum size of the input transistor that you can use. And you cannot increase RD arbitrarily, because if you look at the common mode at the output, the operating point, or what is called the common mode of the output, will be, if this current is I, each of these branches will be carrying current I by 2 in the steady state when there is no input differential applied. And in those conditions, the output voltage will be VDD minus I into R by 2. Right? So if I increase RD arbitrarily to increase the gain GM into RD, then what happens is that the output common mode reduces. So if you increase RD to increase the gain, output common mode will reduce. And if the output common mode reduces, at some point what will happen is the input pair will go out of saturation, and that's when your amplifier will stop working, or basically you'll lose the gain of the amplifier because it won't be biasing saturation anymore. So this architecture cannot be used for very high gains. Okay, it can only be used for low gain, but it has applications when you want to use it for low gain and very wide bandwidth. On Thursday sessions, we'll be discussing these kinds of amplifiers in more detail. But for now, what we are trying to understand is how can we achieve high gain without increasing the power supply voltage. Okay, why did we say increasing the power supply voltage? One of the ways, if you see this output DC voltage here, one of the ways of maintaining this M1 and M2 in saturation while using a fairly large value of RD is to increase the VDD. So if I, for example, if I increase the VDD and also increase RD, then I'll have the same small signal gain GMRD and the same operating point voltage at the drains of the input pair, in which will ensure that the transistors are in saturation and still I get the gain that I designed it for. But that comes at the price of using a higher supply voltage. So basic things of this circuit is that if I want to increase the gain, I can increase the size of this transistors, which is the input pair M1 and M2. If I increase the size, the output capacitance and the input capacitance will increase, which will reduce the bandwidth. So that is one of the issues with increasing the size. You can increase the current, but only to some extent, because eventually once you start increasing the current, what will happen is it will start affecting the output common mode. You have to make sure that the output common mode is maintained at a certain level so that you have the transistors in saturation. Let us say if the input common mode is VCM, then in order to keep these transistors in saturation, what do we need? We need VDS should be greater than VGS minus VT, right? So here what is if this is my source potential Vs, then VDS is basically VDD minus RD by 2 minus Vs, and VGS minus VT is VCM of the input minus the source potential Vs. So essentially this difference, the difference between the drain and the source, should be less than, or between the gate and the drain, the voltage difference between the gate and the drain should be less than one threshold voltage for the transistor to be in saturation. So that puts a limit on what is the maximum current that you can burn, what is the highest value of RD that you can use, and so on. So if you want to increase the gain of this simple differential amplifier without using a very large value of supply voltage, then the only way to do it is to use current source loads. Okay, so instead of putting a resistor RD in as the load, if I somehow put a current of I by 2, if this is I bias, and if I somehow put a current source of I by 2, then what will be the gain of this amplifier? The gain of the amplifier will now depend on what is the output impedance of these two transistors in saturation and the output impedance of the current source. If I assume an ideal current source, the output impedance is infinite. Okay, so if I can somehow put two current sources here, then the gain of this amplifier will become GM into RO, where RO is the small signal output impedance of the NMOS transistor, which is the input transistor in this case. We know that if the transistor is in saturation, the RO will be very high and the gain will be very high. So can we do this? So how can we realize such a circuit using transistors? So one simple way to do it is, so I have the tail current here, which is I bias, which is shown here. What we are generally do is, if you look at this previous circuit, what we have done here is, the tail current is basically taking a reference current I bias and using a current mirror to generate the current source for the tail current. So we can use the same kind of similar kind of current mirror arrangement to generate the current sources of values I bias by 2 and I bias by 2 at the top. So that is what is shown here. So what we have done here is we take this reference current I bias, mirror it once to generate the tail current here in this branch. Use another mirror to generate another copy of this current, which will be flowing through this. So this current will also be I bias. And then use a PMOS current mirror to copy this current from this current sink to a current source. So what this does is this I bias flows it through this PMOS transistor. It develops a VGS across this gate and source in order to sustain that current. And now using a PMOS current mirror, I can generate these currents of I bias by 2. In order to generate this I bias by 2, all that I need to do is, if this transistor has a geometry of W by L, these two transistors each should have a geometry of W by L by 2, half of W by L. Okay, so now what we have got is, in this circuit, we have two current sources on top, each of value I bias by 2, and we have a tail current of I bias. So this gives us this. So we set out to make this kind of a circuit where we have two current sources on top of values of I bias by 2, and one current source at the bottom which will have value of I bias. And we know that if you set up this circuit like this, then the gain of the transistor will be GM into, in this case, it will be GM into output impedance of this current source and the output impedance of this transistor. So basically it will be GM into RON into ROP. Okay, is this clear? So nothing very fancy. All that we have started is, we started with this circuit. This is a simple differential amplifier which you all understand very well. Gain is GM into RD. We want to increase the gain. Increasing GM is difficult because beyond a certain point is difficult, because increasing GM will require very large sizes of the transistor that will limit the bandwidth because of the capacitances that the large transistors will come with. You cannot increase the current arbitrarily, because if you try to increase current arbitrarily, output common mode will become difficult to maintain. If you increase the resistance, then maintaining the output common mode becomes difficult, which means that you have to solution would be to use very high VDDs, which again is not practical. So if you want to increase the gain, all that we can do is, if we can somehow set up current sources as the loads, then we will be able to set up the amplifier to have high gain without using a very high supply voltage. And one of the ways to do it is by using this kind of a current mirror arrangement, wherein I generate two current sources using PMOS transistors for the load, and the tail current is NMOS as usual. By setting up like this, we will be able to generate this amplifier. Now I have a question for you. Will this work? The way we have described it, will it work, or do you see any problem with this? Can anyone think of this arrangement, whether it has any issue or whether you think that it will work? It seems okay.
The tail current should also be sized here.
Tail current should also be sized. So how, in what way you should be sized it? See, tail current sizing we have not disturbed, right? Suppose this is, let's say, W by L of N. This will also be W by L of N. This will also be W by L of N. Same size. So, which means that this will exactly carry I bias.
Yeah. One more thing is, this mismatch can be a problem here actually.
Yes. What is that mismatch problem? Can you elaborate a bit?
Suppose here, if this current mirror, if their W over L changes, or the input GMs changes, right? Input transistor GMs changes, then there could be a common mode gain over here, and it could create a noise problem at the output actually.
Well, that's not quite correct. You are right that mismatch can cause a problem, but it's not the mismatch of the input transistors.
VDS dependency on lambda.
Sorry. Yes.
Lambda, the VDS is depends on lambda, and lambda
VDS
is,
depends on lambda. Okay.
so lambda
So
is a variation. That's why we need to go
again,
for.
I don't think so.
We can use long channel for that. That will not be a problem actually.
Again, I think we are going into some other direction. That's not quite a problem. I mean, lambda, what it does at the most, it reduces the gain a little bit. That's about what. See, all that lambda does is it reduces the RO of the transistors. So it reduces the RO to some extent. Your gain will fall to some extent, but that's not something which I'm talking about. This has some more serious issues. So somebody was mentioning that mismatch can cause a problem. So it's not the mismatch of the input pairs. For example, if this is M1 and M2, even if M1 and M2 are not matched, it doesn't matter much. It will lead to an offset, but that's another problem altogether. There is a more serious issue with this. This circuit will not work. And the reason for that is, again, it is mismatch, but not mismatch of the input pairs, but mismatch of the current sources. Okay, let us see what is the, try to understand what exactly happens. Okay, so transistors fabricated in any process will never be exactly identical. Okay, so what if this is I bias, then it could so happen that in fact it will be that this current which is mirrored here will have some small mismatch between the reference current and the current that is flowing here. Note that I am talking of arbitrarily small mismatch. Okay, it's not, I cannot say that okay, if it is less than 0.001% it will work. Even if it is point not 1, then also there is a problem here. Okay, so if this is I bias, this also will be this current will be slightly different, and the current flowing through these two branches, I bias by 2, also will be having some small error. Okay, let me say this is delta 2 and delta 1. Okay, for the sake of analysis, let me assume that all these currents are perfectly matched, and oops. Okay, let us assume that these currents are perfectly matched. This is I bias, this is also I bias, and this is also I bias by 2 exactly matched. And only problem is that this tail current source here is having a very small mismatch of I bias plus delta. Okay, now what happens in this case is, even if delta is arbitrarily small, what happens is that you have a circuit in which you have two current sources on top which are pumping current of I bias by 2, and you have a tail current which is taking out current of I bias plus delta. So let us say that if the total parasitic capacitance on this output node, including load and parasitic capacitance, everything is some C, then what happens is the current flowing through this KCL at these nodes has to be satisfied. So if I look at any one of these capacitors C, the total current flowing into the node is I bias by 2, and the total current flowing out of the node is I bias by 2 plus delta by 2, right? If I assume that this current splits equally, this current will be I bias by 2 plus delta by 2, and similarly this current will also be equal to this current. So I have a situation in which the capacitor output capacitance of this transistor, of this amplifier, is being injected with current I bias by 2, but what we are taking out is I bias by 2 plus delta, which means what will happen is that the voltage across this capacitor will keep dropping. At what slope will it drop? It is basically V is, what is the voltage across the capacitor? Integral of I into time, and that we know that the current flowing out of this is basically exactly equal to delta by 2. So what it means is that both the output nodes voltage will keep dropping at a rate determined by the value of the capacitance and the mismatch here, which is delta, and because it's split into 2, and assuming that it is split equally, the split will be delta by 2. As the voltage keeps dropping, at some point what will happen is the input transistors will go out of saturation and your amplifier will stop working, giving you any gain. Okay, notice that I have not assumed any, it's not, there's no smallest value of mismatch that the circuit can sustain. Even if I by 2 is delta is arbitrarily small, this problem will still be there. You can never match two current sources to be exactly of the same value in any process. So this circuit will not work. It will eventually discharge the output till the input pair M1 and M2 go out of saturation. Similar thing will happen if the mismatch is on the PMOS side. Okay, let us say the source, the current that is coming from top is slightly more than I bias by 2. Then what will happen is that the output, the voltages at the output nodes will keep increasing at a constant rate, which is determined by the mismatch delta. Okay, and when it keeps increasing, what will happen at some point, the current source transistors, PMOS current source transistors on top, they will go out of saturation, and again once they go out of saturation, you will have low impedance and therefore your gain will reduce. So it doesn't depend in which direction the mismatch is. One of the transistors, if the mismatch is on, if the current in the lower branch is high, then the input transistors will go out of saturation at some after some time, once the voltage reaches voltage drops to that to a certain value, which is determined by the common mode and input common mode. And if the upper current is high, after some time, the current sources on top will go out of saturation, and once they go out of saturation, it doesn't matter which, once one of the two transistors goes out of saturation, the gain will fall. So this is which is why we will never be able to practically make this circuit work. Okay, even if you say that I'll carefully tune it, once the temperature changes a little, small mismatch will happen and the transistors will go out of saturation. Okay, so this circuit will work correctly only if the tail current is exactly 2 times the current source load value. So basically only if this, or basically in this case, if only if delta is 0 will this circuit work correctly. Okay, any small mismatch, however arbitrarily small, will result in the output either charging up till the current source load goes out of saturation, or charging down until the current source at the tail or the input, not tail as such, or the input pair goes out of saturation. Once that happens, the gain will decrease and the differential amplifier will not work as expected. Okay, so basically if somebody was asking, can I repeat? So basically the thing is like this. If you look at the circuit, look at this output capacitance, what is happening is you have a output capacitor here. It is being charged by some current I bias by 2. It is being discharged by some current of I bias by 2. Okay, if there is a small mismatch in either of these, if this becomes plus delta, or if the tail of the sink becomes different from I bias by 2, that difference current has to flow through the capacitor, and that will cause the capacitor voltage to either rise up linearly or fall down linearly, depending on the direction of which one is higher than the, whether the source is higher or the sink is higher. And that will result in the output common mode either increasing or decreasing till one of the two transistors goes out of saturation, and that will basically kill the gain. Okay, so then how do we construct a fully differential amplifier with high gain? So how can we solve this problem? So essentially what we have to do is, the way to do it is to somehow actively track the operating point and bias the current source accordingly to keep the transistors in saturation. You cannot do it by design. Okay, when I say you cannot do it by design means, while designing this, you cannot say, okay, I will choose a certain W while for this. By fixing the geometry, you cannot, at design time, you cannot ensure that this circuit will work. This will definitely not work. Okay, so if you have to design such a circuit exactly for it to work, you have to somehow actively track the operating point, check using some kind of feedback mechanism, check whether it is actually going out of saturation, and detect it and correct for it dynamically. Okay. So what is it that we should check? So from our discussion, we see that whenever there is a mismatch, it's the output common mode that either drifts up or drifts down, depending on the direction, on the which current is higher. If the current source is higher, it will go up. If the current sink is higher, it will go down. Okay. If we can somehow sense this common mode, okay, if we can somehow sense the common mode and adjust the current dynamically, if you see that the current output common mode is going up, you start decreasing the source current. If you see that the output common mode is going down, you start increasing the source current till you maintain the common mode at the desired value. If you can somehow set up such a circuit, then we would have achieved our desired objective of keeping all the transistors in saturation, and that will make sure that we get a high gain. Okay, so how do we do that? So let us look at this circuit. So essentially what we know is, now if we have a mismatch, what happens is the output common mode drifts. Okay, it either drifts up or down, depending on whether the tail current is high or the current source is high. So if we have to dynamically bias the circuit, basically what we need is, we cannot use this kind of a bias arrangement. We need to somehow derive the bias of this PMOS current source VBP in such a way that it actively tracks the common mode. Okay, so what I mean by that is, what is VO plus? Basically it is VCM plus the small signal output, or probably what I should say is VO plus was the small signal value. If I look at the total voltage here, it is basically output common mode plus VO, and the voltage here will be output common mode minus the small signal output voltage V0. So if I have to detect the mismatch in the source and the tail currents, essentially what I need to do is, I need to see how the common mode drifts. So how can I detect the common mode? So to detect the common mode, all that I need to do is, I need to take the average of these two signals. Okay, so if you take the average of VCM plus V0 and VCM minus V0, what will happen is, V0 will get cancelled because it is having positive and negative signs on the two nodes, and what I will get here is the VCM of the output voltage, right? So even in the presence of a differential signal, if I take the average of the two outputs, I will get the common mode signal. Now what I need to do is, I'll take this common mode, I will compare it with some reference common mode. Okay, so for example, I know the VCM of the input. What is the input common mode? Based on the input common mode, I know what should be the output common mode DC value so that the transistors are in saturation. I measure the common mode, compare it with the reference common mode in order to see, to make sure whether the transistor is in saturation, and you drive this VBP with this error signal with some gain. Okay, this is like a standard negative feedback circuit. What you are doing is, you are trying to, generally what we do in a negative feedback circuit is, if you have some gain here, and what we do is, we take the input, subtract it from the output, and this is a standard negative feedback circuit, right? And this is what we know is this error voltage. If the gain is sufficiently high, then we know that this negative feedback loop will drive this error to 0. That is exactly what we are doing here. We are taking sensing the difference between the input common between the detected output common mode, the reference common mode, and amplifying it and driving this with the hope that the negative feedback will drive the error between VCM and VCMRF to 0. Once that happens, basically your job is done. So let us just analyze whether that happens and ensure whether the signs that I put in are correct. Okay, let us say that there is a mismatch now. Okay, let us say the tail current is more by some delta and the current source is basically having a value of I bias by 2. What will happen if the tail current is more? If the tail current is more, what will happen is VCM will, the output common mode, detected output common mode will decrease. If the detected output common mode decreases, what will happen is this amplifier output here, what will happen is if the negative terminal decreases, basically this current will increase. Okay, so if this increases, this current will fall. Okay, so basically what I need to do is this sign should be positive. Okay, yeah, I think that will be fine. So basically VCM will decrease if the positive term in voltage on the positive terminal reduces with respect to the reference. Then what will happen is this voltage will fall. If this voltage falls, what is happening is basically the VGS is of this transistor is increasing, which will result in this current to increase. Okay, so basically what we have seen is if the tail current is slightly more than what it should be, then what will happen is output common mode will fall. If the output common mode falls, this amplifier's output will also reduce because basically what will happen is VCM detected will become less than VCM def, and once that happens, this output common mode will fall, and if the output common mode falls, this current, the bias point of this current source transistors will reduce, which will increase the current in the PMOS transistors to stabilize the output common mode. Okay, so the same thing other way around will happen if the tail current is slightly less than the source current. So by setting up a negative feedback loop like this, we can make sure that all the transistors will always be in saturation without using any without having any problems of mismatch. Okay, suppose the temperature increases, and because of the difference in the behavior of the PMOS and NMOS, let's say again one of them has a mismatch. This feedback will dynamically track that and make sure that the source current and the tail current is always exactly balanced, so that the amplifier is biased in saturation and you keep getting the high gain that you wanted to get. Okay, is this clear? Any questions about this? Okay, so quickly I'll just go through what we have discussed now is simple differential amplifiers with resistive loads. It's difficult to get very high gain without increasing the power supply voltage, which is not practical. The way to get high gains is use a current source load. If you use a simplistic current mirror approach, this will not work because yes, Miss Rupa, you want to say something? Okay, so if you use a simplistic approach of using current mirrors, what will happen is any small mismatch will take one of the two transistors out of saturation, and that will basically kill your gain. Okay, so the way to do it is to bias the transistors. This will not work, of course. The way to do it is to bias the transistors actively by using some kind of negative feedback. So what is that negative feedback? Basically, you detect the output common mode by taking the average of the two output signals. If you take the average, you will get is the common mode of the output. Compare it with the reference common mode and drive the PMOS current sources in a negative feedback to make sure that your output common mode always stays where it should be. Okay, so that's the same circuit that we have shown here. We need some kind of common mode sensor. Basically, common mode sensor is nothing but it's a circuit which takes the average of the two signals and then drive it in a negative feedback. I think the signs here also should be inverted. Okay. So how do you detect the output common mode? One of the simplest ways of detecting output common mode is just to use two resistors. Okay, if you just use a simple volt resistive divider, if this is VCM plus V0, and this is VCM minus V0, then what you will get at the midpoint of the two resistors is the output common mode. This is a very simple way of detecting the output common mode. Okay, however, if you use two resistors like this, then what will happen is these two resistors will load the output and it will reduce your gain for the differential input signals. Let us see how that happens. So this is a circuit that we have. So the simple differential amplifier with current source loads, I am using two resistors to detect the output common mode and comparing it with a reference to drive it in a negative feedback. Okay, so what I have shown in red is the AC ground. So for small signals, this node, and this node are all at AC ground, are all at ground. So if you look at the small signal equivalent, the gain of this is basically GM into the output impedance seen at the two output nodes, right? So in this case, what will be the output impedance? It will be, because this midpoint is at AC ground, it will be the R that you put to detect the common mode in parallel with the output impedance of the current source. In fact, it should be ROP parallel to R1, right? So basically what this will do is it will reduce the output impedance from ROP parallel to R1 to ROP parallel to R1 parallel to this small R that you, or the R that you put for detecting the common mode. So basically the gain will become almost equal to GM into R, assuming that R1 and ROP are much larger than R, which is generally the case. Okay, unless you use a very large value of R to detect the common mode, the gain will definitely fall. And it is not practical in CMOS processes to have very large values of resistors just for detecting the common mode. So that is one of the main problems with this, but that's not the only problem. What is the other problem with this? Another serious issue is stability of the common mode feedback. Okay, so let us look at the transistor level diagram of the common mode feedback loop. So this is the same thing. In the previous figure, we had shown this amplifier is just a simple using a symbol of the op amp or any single stage amplifier. What we have done here is we have actually put it in using a simple differential amplifier for implementing the common mode feedback. So this is a simple amplifier which takes the difference of these two inputs and produces a gain times the output, which then drives the PMOS transistors in the feedback loop. Okay, so if you look at this circuit actually looks similar to the two-stage op amps that we discussed yesterday. Okay, so what we are interested in finding, this is a feedback loop. We want to see whether the feedback loop has any stability issues. So if you look at the common mode equivalent of this feedback loop, so essentially what I'm saying is if you disconnect all the DC, all the differential inputs, connect only the input common mode to both the transistors, then this amplifier will be exactly same as the two-stage amplifier that we looked at earlier. A two-stage amplifier in which you have a differential input and a single-ended output. How does that happen? So let's look at the second stage carefully. The second stage basically has two transistors, both are in parallel. Input is also in common mode, so these two are also can be reduced, and the output is also symmetric. So if you draw the common mode equivalent, we can replace this with a circuit which looks like this. So if this is W by L of P and this is W by L of N, we can replace this circuit with one PMOS transistor which has 2 times of W by L. Okay, then one NMOS transistor which again has 2 times W by L of N, which is W by L of P, and of course the tail current which gives you the bias, and this is connected to V in CM, and this is connected to VBP. And from here what you have is, you have a resistance of R by 2. So basically, these two branches are driving this particular node through a resistance R. Okay, both the branches are identical, therefore I can combine them and draw an equivalent circuit which looks like this. Right? Since both the stages are identical, I can combine the two stages, and both the resistances will then appear in parallel. And if you simplify it, you can reduce it to a resistance of R by 2. Okay, now if I take this, that's what we have shown here. This is R by 2. So now if you look at this circuit, this is exactly same as the two-stage op-amp that we have used, which is now connected in feedback with the resistance R by 2. Okay, so this will have the same problems that we discussed yesterday. The first amplifier will have a output capacitance, because of which it will have a pole at the output. This second amplifier will also have a pole at the output, and if these two poles are close to each other, then this amplifier will have a tendency to become unstable if the poles are so close that the phase margin is actually not sufficient for stabilizing. So how can we stabilize this loop? We can use any of the techniques that we discussed yesterday. We can stabilize this loop, for example, by using a Miller capacitor. But how will you put the Miller capacitor? Basically, in this case, this is the complete diagram. So what we had done yesterday, if you recall, we had a stage 1 with a differential input and stage 2, and we put a Miller capacitor basically between the output of the and input of the second stage. In this case, the second stage is basically split into 2. So you will have to basically put 2 capacitors from here to here, which is shown in red, and here to here as shown. From here to here and from here to here. Okay, but this is not something that is desirable. Why? Because any capacitance that you put at the output of the differential amplifier will also affect the bandwidth of the amplifier in differential mode signals. So basically what we are doing is we are putting a capacitor here to stabilize the common mode feedback loop, but that also affects the bandwidth of the amplifier for differential signals. This is something which is not desirable. So generally we don't do this. What we do is, instead of putting a Miller capacitor, we just put a large capacitor out at the output of the first stage. Okay, so what that means is, you have a differential amplifier A1, another amplifier A2, which forms your two-stage amplifier. Normally what we have done for two-stage op-amps is we use a Miller capacitor. But now, instead of using a Miller capacitor, what we are doing is, what a Miller capacitor does is, it gives you A2 times C, right? That's what, if I put a capacitor C, what the Miller effectively gives you is, it gives you a capacitance A2 times C here, and something which is almost equal to C here, which splits the two poles of the op-amp. Now, in this case, doing that basically it reduces the bandwidth of the amplifier for differential signals. So what we do is, instead of putting a Miller capacitor, we directly put a capacitor here of a sufficiently large value in order to stabilize the loop, and nothing at the output is required. So that is what is shown here. Okay, basically we are just putting a capacitor at the output of the common mode amplifier to shift its pole to a lower frequency so that the common mode feedback loop is stable. Okay, any questions here? This is nothing new. What we have discussed yesterday, two-stage op-amp compensation, the same thing, only it's coming in the common mode picture and not in the differential, not in the picture for the differential input.
Professor Naveen, means
Yes.
this configuration will decrease the gain, I think, right? Because of R, I think.
Yes, it will reduce the gain. We will come to that. Gain reduction
And
is one problem. Stability is a more serious problem. So we have now looked at how to stabilize. How to detect a common mode without affecting the gain, we will look at that now.
And actually, we are using this feedback, this op-amp to solve the mismatch problem, right?
Yes.
So what happened that if this feedback op-amp is also a mismatched kind of thing?
It doesn't matter.
It doesn't matter.
What kind of mismatch? Let us say. What can happen in feedback loop? Let us say the op-amp was designed for a gain of 20. Because of mismatch and this and that, let's say it had a gain of 18. What will happen? Nothing will happen. What will happen if the finite, there are two things. One thing is mismatch, which results in the reduction in the gain of the common mode feedback amplifier, or if it has an offset. Both of these will have a very negligible effect on the output. What will be the negligible effect? Let's go back to our block diagram picture of, yeah. Okay, so what will this negative feedback loop do? Basically, it will try to reduce the error between VCM and VCM ref, right? It drives this difference to 0. What will be the steady state? In steady state, what will be the difference between these two nodes? It will depend on the gain of this amplifier, which we are putting here. Okay, if this gain is infinity, it's just like this standard op-amp arguments. If the open loop gain of this op-amp of this amplifier is infinity, then the difference between this VCM ref and VCM detected will be exactly equal to 0. If it is something less than infinity, it will be some small finite difference depending on what is the gain. Okay, that gain in this particular circuit is not very crucial. Why? If you have a gain of 100, it means that you will have an error of 1%. If you have a gain of 10, you will have an error of 10%. Even if you have a gain as low as 10. Okay, 10% error, what does it mean? Let us say your VCM ref is supposed to be 900 millivolts. Okay, it means that once the circuit settles, this voltage difference will be somewhere around 810 millivolts. Basically, it will have a difference of 90 millivolts between the two. Okay, 810 millivolts it will settle at, but still the output 810 millivolts could still be sufficient to keep all the transistors in saturation. Okay, that's so basically the finite gain of this amplifier will not have any problem. Let us look at other thing. Suppose there's an offset. Suppose the amplifier A has an offset of input referred offset of, let us say let me take a very large value, let's say even 10 millivolts. What will it mean? It will just mean that the final value at which the output common mode settles to will have an offset of 10 millivolts. 10 millivolts is nothing. When you are looking at common mode picture, 10 millivolts error won't produce anything. So even if this feedback loop is not perfect, when I say what kind of imperfections, there are only two kinds. One is gain, one is offset. Third is a speed. We'll come to that speed later. Basically, speed also we have discussed. Basically, we need to make sure that this feedback loop is stable by putting the compensation capacitor. So it's not much of a problem. The only issue is what remains is that these two resistors will reduce the gain. So we need to have some smarter way of detecting the common mode. There are many ways of doing that. We will discuss that in the remaining part of this session. Is that okay?
Yeah, understood. Thank you.
Yeah, okay. Now I have a question. Is the dynamic performance or the bandwidth of the common mode feedback loop important? Okay, we have seen that the feedback loop is unstable. We stabilized it by putting a Miller capacitor. So basically what does a Miller capacitor do? It just basically stabilizes the amplifier loop by reducing the bandwidth. So is the bandwidth of the common mode feedback loop important? Okay, so what I'm indirectly what I'm asking is, if there is any mismatch in the tail current source and the current source on top, the output common mode will change, correct? Your feedback loop will detect and correct it. Is the speed of this detection important?
Yeah, it is important.
Why do we say that? Okay, let me put the question in another way. How fast is good enough? How fast should it be? Should it be like microseconds, nanoseconds, seconds? How fast can it be? Or how slow can you afford to make it? Because the moment you put a stabilizing capacitor, it will reduce the speed of the feedback loop. Is that a concern? That's the question.
Actually, it will depend upon the load capacitor here. And then
load capacitor, what do you mean by load capacitor? Generally, when I say load capacitor in the differential amplifier, it's the load at the output of the
at
differential
that
amplifier.
side. Exactly.
Why will that be a concern? No, see, essentially what this amplifier will have two poles. One is the output pole here. Let me call this as P1, and the second pole will come because of the load capacitance on the output. So let's say this is some P2. By putting this Miller capacitor here, what you're making is you are basically pulling P1 to be much smaller than P2. That is what the Miller capacitor is doing.
Yeah, Professor, but we don't expect very good
Not Miller cap,
detection here.
Sorry?
Means this configuration will not good enough for the speed or something like that. We need to compromise on that actually.
No, I don't think so. The differential amplifier, if you look at if you see this circuit has two modes. One is the differential mode, one is the common mode. For differential input signals, the bandwidth is only determined by what is the output impedance on this node and the load capacitance.
Yeah.
So that load capacitance we are not touching. Whatever is native capacitance is there, that is there. We are putting a stabilization capacitor on the output of the common mode amplifier, common mode error amplifier. That reduces the speed of the common mode feedback. It doesn't do anything to the differential amplifier. Okay, so the answer is that it's not very crucial, because we are looking to adjust the bias of current sources to make sure that the current source value and the current sink value is exactly balanced. Now, the changes in these current sources happen because of temperature, because of process variation. Process variation is a one-time thing. It's a DC thing. Temperature changes, or maybe supply voltage changes, or reference itself drifts. Those drifts are very slow. They happen with time constants of seconds. So even if your common mode feedback loop settles in, let's say, a couple of milliseconds, it is still fine. It doesn't affect your overall dynamic performance of the amplifier for differential input signals. So the common mode, the speed of the common mode is basically, the common mode feedback is there to track the changes in the currents which happen with very slow time constants. Okay, typically a few hundreds of milliseconds at best. I mean at worst, if the temperature of the IC suddenly changes because of some increase in power consumption in some side of the circuit or whatever, that generally takes a few milliseconds to temperature changes generally happen very slowly with respect to the speed of signals we generally deal with in electronics. So this common mode feedback loop speed is not that crucial. The second question I have is, does the CMRR of the differential amplifier depend on the performance of the CMFP loop? We are doing something to the common mode feedback. Does the common mode rejection ratio of the amplifier depend on any performance parameter of the CMFP loop? Let's say the open loop gain or the bandwidth of the common mode feedback?
No, I think.
No, because the input common mode, if you look at if there is any common mode noise on the input, its effect on the output will only depend on how good this current source is, how high the output impedance of this current source is. So it doesn't affect the common mode rejection ratio of the op amp itself. Okay, the only problem with this is that the two resistances that you have put to detect the common mode will reduce the gain of the amplifier, and therefore we should look for a better way of detecting the common mode. Okay, fine. So what are the better, as we have seen that the resistances limit the gain of the amplifier, and putting very large resistance values is difficult in CMOS processes. So other common mode feedback detectors we need to look for, which do not need large resistors. One simple way is we could use source follower buffer followed by a simple resistive common mode detector with smaller resistance values. So essentially what that means is you have the differential amplifier. Okay, I have not shown the differential amplifier here. So you have this differential amplifier which has these two output nodes at VCM plus V and VCM minus V naught, right? And I want to detect the common mode. So one of the ways is you take these two signals, VCM plus V and VCM minus V, you pass it through to source follower buffer. So what is this? This circuit is nothing but a source follower buffer. So basically it's something like this, right? So this NMOS is a current source, and this is a simple NMOS based source follower amplifier. Output is taken at the source node. So the output impedance of this is almost equal to 1 by GM, right? So we are all familiar with the simple source follower amplifier. It has a gain of almost equal to 1. Therefore, what will the voltage here be? The small signal voltage will be almost equal to V, and the DC voltage will be basically VCM minus VTH, right? So this is what will happen at the output. Basically, the input will be shifted by one threshold voltage, and the gain will almost be equal to 1. So this node will be at VCM minus VTH plus some small value, the small signal V. And the output impedance of this is almost equal to 1 by GM. Similar thing here on this side. What will happen here is you will have VCM minus VTH minus V, and again the output impedance is almost equal to 1 by GM. Okay, now you can use two small values of resistance. Even if I use two small values of resistance, even if something, even if I use some value close to 1 by GM also, it doesn't load the amplifier output, right? Because the amplifier output only sees the input capacitance of these two transistors. It reduces the bandwidth of the amplifier by a very small value, which depends on the size of the transistors that you use for the source follower buffers. You won't use very large sizes because this amplifier is not supposed to be very fast. It is only supposed to detect the changes in the common mode. So now if you have this source follower buffer, what you will have here is you will have the common mode which is detected. Because the detected common mode will have a shift of one threshold value, what we do is we take the reference common mode and also pass it through a similar source follower buffer, which will give me VCM ref minus VTH. Now I can use the same amplifier to measure the difference between these two detected common mode and the reference common mode and drive the feedback loop. Okay. So in this way, we can make sure that the amplifier output is not loaded. Therefore, the differential gain doesn't change, but you detect the common mode and drive the common mode feedback to keep all the transistors in saturation. Now, again, is this the best way to do it? Are there any problems with this? The problem comes with linearity. So the linearity of the source follower amplifier will affect the dynamic range of the amplifier for differential signals. So why is the linearity of this amplifier important? The linearity of the source of the common mode detector. Okay, let us see what happens if this common mode detector is non-linear. So what is the common mode detector supposed to do? It is supposed to take the average of the two signals, and the average will be equal to the common mode that is present at the input. So if you have a amplifier of this source follower buffer which is non-linear, so this is just a sketch to illustrate what the problem is. So the input is some VCM plus V and VCM minus V. Okay, some two signals which are out of phase with a common mode of VCM. These two signals, when they go through the non-linear source follower buffer, they will get distorted by some. Basically, they will get distorted because of the non-linearity. Okay, I have shown the non-linearity by showing the output getting saturated, and the saturation will be different in the upper side and the lower side because of the non-linearity. Now, if you take the average of these two, you will find that the average of these two will not be equal to VCM. In fact, it will have some kind of component which is at 2F. Okay, now that component, basically this will produce a, if you look at the overall feedback loop, what is happening is, let me go back to the block diagram representation. So what is happening is, if you have an input signal at some frequency f, the common mode the detected common mode, because of the nonlinearity of the common mode sensor, will have harmonics of f, which will be at 2f, 3f, and so on. That harmonic will now appear on the bias signal after getting amplified by the gain of the amplifier, and that again will come and appear at the output. So that is how the non-linearity of the common mode sensor will produce distortion on the output for the differential signals. Okay, let us try to mathematically look what is the source of this. Okay, the two differential signals can be written as VCM plus V and VCM minus V, and the output of the nonlinear common mode detector can be, in general, without any problem, can be written as some f of VCM plus V plus VCM minus V. This all said and done, this block still takes the average of the two signals, and here f of x is the non-linearity of the common mode detector. In this case, we are talking of the non-linearity of the source follower buffer. What happens because of the non-linearity? The non-linearity can be expressed as can be written as this. So f of VCM plus V can be written as some alpha 1 into VCM plus V plus alpha 2 into VCM plus V the whole square plus alpha 3 into VCM plus V the whole cubed, and so on. So basically, the non-linearity will generate harmonics of the input signal. Similarly, f of VCM minus V. Okay, it will, assuming that the two source follower buffers are matched, the coefficients alpha 1, alpha 2, and alpha 3 will be equal. Now, when you take the average of these two signals, what you'll get is, you can basically plug this into this expression for the VCM detector output and simplify. So basically, what will happen is, you will get alpha 1 times VCM. Okay, this 2 will get cancelled. You can expand this square term. What will happen is, you will get something alpha 2 times VCM squared, which will appear here. Alpha 2 times V squared, which will appear here. There is a term VCM into V, but that will have a positive sign here and a negative sign in the second expression. That will get cancelled. Okay. Similarly, you can just simplify it. I will not go through all the steps, but you will get basically all the different harmonics of the common mode signal and the AC input differential signal, which is V. Okay. So if you see this, what sustains at the output is the even order harmonics of the input signal. If you recall, when you have a differential amplifier and you take when you subtract two signals, all the even harmonics get cancelled and odd harmonics remain. Now we are taking the average. You are adding the two signals. So what is happening is all the odd harmonics are getting cancelled and the even harmonics remain. That is for the differential input signals. But when it comes to the common mode signal, that is common to both the things. You get the even as well as the odd harmonics of the common mode signal. Okay, so all these things will now appear at this messy signal with all kinds of components will appear at the bias of the current mirror, and that will then get modulate the current, which will change the output voltage according to this kind of nonlinear expression. Okay, ideally VCM is a DC signal, right? So VCM is a DC signal, which means that all this VCM squared, VCM cubed and all is expected to be a DC signal, and then when the loop settles, you know that the common mode, the small signal common mode is 0, which means all these VCM components should disappear. However, the harmonics of the small signal on the common mode, which appear because of the input differential signal, result in a common mode which will have a small signal variation, and that in turn will get will go through the loop and make matters worse for you. Okay, what I'm trying to say is like this. Let me go back to this amplifier again. What we are saying is there are two things. Let me take the simple example in simpler case in which, let's say that the common mode detector is linear. There is no non-linearity from the common mode sensor, but this amplifier A is non-linear. Will that produce any problem? No, it won't produce any problem. It's just that the way this amplifier drives the error to 0 will be slightly distorted, but eventually the output error will go to some fixed offset value, which will then remain there. So any non-linearity of this amplifier A will not affect the dynamic performance of this amplifier. But if there is a non-linearity in the common mode sensor and a non-linearity in the amplifier, then because of the non-linearity of the common mode sensor, there will be a small signal variation on the common mode detector output, and that small signal variation on the common mode detector output will go through the non-linear amplification of the amplifier here and produce a further distorted signal on the bias point. This will then get translated to a non-linearity, some kind of distortion in the common mode of the output. So basically, all that we are trying to say in this long run argument is that the linearity of the common mode detector is rather important for the distortion performance of the differential amplifier for differential input signals also. So therefore, it is very important that the common mode detector that you use has the desired amount of linear range. Speed is not important. So you can sacrifice speed, but you should make sure that you design your common mode detector and error amplifier to have very high linearity. How much linearity? That depends on what is the dynamic range of your differential signals that you are looking to design for. Okay, what I'll do is in the remaining 15-20 minutes, I'll just go through a few other common mode detectors. What we have done is, this is the similar common mode detector that we had seen earlier. Instead of using, what we had done earlier is we took two source follower amplifiers and used a resistive divider in between, right? This is what we had looked at in the source follower amplifier based common mode detector. In this case, what we have done is we have eliminated these two resistors and directly shorted the oops, what happened? Yeah, and directly shorted these two. Effectively, they are the same. So basically what happens is, if I look at this source follower amplifier, I can represent it as an amplifier with a gain of almost equal to 1, followed by output impedance of 1 by GM. Similarly, the second stage, this right side amplifier can be represented as a amplifier with a gain of almost 1, followed by a resistance of 1 by GM. Now, when I tie the outputs of these two together, basically it looks like a resistive common mode detector, but instead of having physical resistors, you are using the implicit output impedances of the two common source, of the two source followers. That is all what is happening here. But is this better or worse than the previous one? Of course, it uses fewer components, but the source follower amplifier, this particular configuration has inferior linearity performance as compared to the previous one. Because in the previous case, what was happening is the current through this transistor was held constant by this bias current IB, and because this had a gain of almost 1, the voltage difference between these two was fixed as 1 VTH, right? Because the source also will swing in sync with the gate with a DC shift of 1 VTH. But in this case, what is happening is the output is at the common mode detected, but the input is swinging from VCM plus over as a sinusoidal signal over VCM, which means that the voltage across the gate and the source will not be constant. And when the voltage is not constant and it swings up and down, what happens is the GM changes, and that changes the resistance, and therefore it changes the linearity. It affects the linearity of the common mode detector. Okay, so this has inferior performance to the source followed by resistive buffer, but it is used depending on what kind of dynamic range you're looking for. You can use one of all these configurations. Okay, I have discussed this. So next is source follower amplifier using a current summing amplifier. This is again a very simple circuit. So essentially what happens here is, let us say this is VCM plus V and this is VCM minus V. At steady state, if this current is I, this will be I by 2, this will be I by 4, this will also be I by 4. For a small signal VCM plus V, what will happen is this I by 4 will increase by some small amount delta, and for since the gate input for this transistor here is VCM minus V, this current will decrease by some small amount minus delta, and the total current through this transistor will still be I by 4. Okay, so for differential input signals, this amplifier doesn't do anything. If the input common mode changes, if this common mode itself increases, then what will happen is each of these currents will increase from I by 4, which will result in increasing of this current from I by 4, which will then follow the negative feedback action and basically produce the bias, adjust the PMOS bias to ensure that the loop settles. Okay, so this is a simple summing amplifier. What happens is the current through this branch, let me show it the current through this branch basically will be GMN into V plus GMN into minus V, right? So basically it performs the function of averaging. So GMN into plus V will flow through one transistor, GMN into minus V will flow through the other transistor. When you add the two by tying them up together here, you get the average. So this circuit gives you higher gain for the common mode feedback, which means that you will have a lower steady state error in the common mode feedback loop. But again, you have to design this amplifier, so that this summing amplifier, so that you have the desired linearity to make sure that your overall differential amplifier has the required linear range that you want. Okay, yet another one. Again, a circuit which has very high linear range. Basically what we are doing here, this is similar to the source follower buffer, but instead of using a simple source follower, we are using complementary source followers. So what that means is, generally what you do in a source follower is you take an NMOS and you bias it with a current source, or if you want a PMOS current source follower, you take a current source and put a PMOS transistor here. So what this does is, in this case what we do is, using complementary source follower buffers, we merge these two circuits and use a buffer which has a NMOS down and a PMOS, NMOS up and PMOS down. Okay, this circuit, what will be the DC shift in this case? In this case, there will be a DC shift of minus VTH. In this case, there will be a DC shift of plus VTP. right? So when you put them both together, what happens is that the overall DC shift between input and output is basically only equal to the difference between VTP and VTN. Generally, processes are designed so that VTP is very close to VTN, so which means that the DC shift between input and output will be very small. And recall that this amplifier has a gain of, this is like a inverter with which has an, instead of PMOS up and NMOS down, we are using NMOS up and PMOS down, has a gain of almost 1, and dynamic range is also very good. So this, if I plot V out versus V in of this, you will see that the dynamic range of this amplifier is very high. So this is one way to generate a common mode feedback loop which has very high dynamic range, or very high linearity, in other words. So what is done is you have one source follower amplifier for the positive input, one for the negative input, tie them up both together, so that will basically produce the averaging through the output impedances of these two source followers. That will give you the VCM detected. And for keeping symmetricity, what you do is you pass the reference also to the same kind of buffer, and then you compare and drive the error signal. Okay. Yet another way of doing it is using current transistors in triode region. Okay. Again, this is a simple circuit. To understand the circuit, what I'll do is I'll first take the circuit of a simple current mirror. With degenerating resistors. Okay, so if I have a current mirror, and okay, let me not put two resistors for simplicity, I'll just put one resistance at this side. Okay, suppose this current is I, then what will happen is this will set up a voltage VGS in order to flow that maintain that current I through this transistor. Assuming these two transistors are matched, what will happen is this node potential will be I out into R2, right? If this is I out. Okay. So what will be I out? I out will be basically mu n C ox W by L 1 by 2 into VGS. VGS is nothing but VGS of M1 minus I out into R2 minus VTH. Right. So basically what will happen is this current I out will reduce if I increase the resistance here, because if I put a resistance here, effective VGS of this transistor is getting reduced, and that is going to modulate the current. So we are using this kind of configuration in which you adjust this current R2 resistance R2 in order to get the desired kind of current at the output. So that is what is done here. So what you have is so this part, is the standard differential amplifier. You generate some bias voltage VBP, which will give you the desired source current of I by 2. And if I size this so that to get a current I, this branch will flow current I, that is mirrored to this to flow current of I. Now what you do is you degenerate this diode current connected current source with a transistor biased in triode region, which is driven by VCM ref. So these two are in triode. So there will basically be a resistance which is a function of VCM ref, right? Here on this side, what you do is you use two resistances which are connected to VO plus and VO minus, right? So this is VO plus and this is VO minus. So what will happen is these two are biased in triode region. So one of these, if VO plus increases, one of these resistances will increase, the other one will decrease. And what you get at the summing node is basically the average of these two. And this circuit will make sure that the average resistance of these two transistors in triode is equal to, or rather the VCM here is equal to the VCM here. because if there is any difference, one of these two resistances will be different from the other, and that will cause either cause this current to increase or this current to increase in order to maintain the output common mode. Okay, again, it's a simple circuit. You can spend some time analyzing it. If the output common mode increases, what happens is this resistance will increase. If this resistance increases, what will happen is this bias current will fall. That's all that is there to it. Okay. So here again, the transistors are in triode, so generally they have a good linearity. But if VO plus and VO minus become very large, what will happen is, you remember the equation of resistance of a transistor in triode, right? Only if VDS is very small, the transistor acts like a linear resistance. Otherwise, it will also introduce some kind of non-linearity, and that will again affect the output common mode and also the different linearity in the differential picture. Okay, this circuit generally has somewhat low common mode gain of the feedback loop compared to the previous ones that we had seen. Okay, this is done. So that is what we have. So if I just quickly maybe look at what we have discussed in this session. Okay, so basically what we want is, we wanted to make differential amplifiers which have differential output. We cannot do it using resistors. We need to use some kind of current sources in order to get high gain. Simply putting current mirrors to generate a current source won't work, because with mismatch, the output common mode will drift and the amplifier will stop working as an amplifier. We need some kind of feedback circuit which will detect the output common mode and drive it actively to maintain all transistors in saturation. So one of the ways of detecting is using two simple resistors, but that reduces the gain. Not just that, it also affects the stability. So you have to make sure that you stabilize the common mode feedback by putting appropriate, by putting appropriate compensation capacitors to split the poles of the loop of the common mode feedback. Okay, then we looked at other problem, which is the resistance reducing the gain. We need to have better common mode detectors. So we have seen various detectors. One is using the source follower buffer without explicit resistors. The next thing what we saw is using current summing amplifiers or using transistors in triode, and I think there was one more, which is this, which is using complementary source follower buffers. So I hope that gives a good overview of how to work with fully differential amplifiers. What are the standard basic problems that one might encounter while doing these kinds of circuits, and how to address them, and a few variants of how to detect common mode. Okay, so many of these circuits are standard and available in most of the standard textbooks. So most of the things that I've discussed in this session can be found in Analysis and Design of Analog Integrated Circuits, which is Gray and Mayer's book, or CMOS Circuit Design, Layout and Simulation, which is Jacob Baker's book. And if you want to look at more kinds of common mode detectors, you can look at this reference, which summarizes various types of common mode detectors, many more than what we have discussed here, and analyzes their linearity and so on. Okay, any questions? If not, what we'll do is we'll take a break before we resume for the second session. The next session will be on voltage reference circuits by Dr. Vinayak. If there are no questions, we'll stop here and take a short break for 15 minutes. Maybe you can have some tea or something and come back. Okay, thanks. I will upload this presentation in some time. Okay, thank you.